All right, ladies and gentlemen, it's time to get into some polygons, four-sided ones to be exact, which we will call quadrilaterals. And we're going to get into so many different types of quadrilaterals, you just won't know what to do with yourself with all the excitement. So when we're naming a polygon, much like we're naming a triangle, we do with the three letters, the three vertices, the same kind of idea here. Let's say that this guy's a parallelogram. Let's just say it's a parallelogram. So I'll draw myself a little mini parallelogram. Whoop. There we go. And then I'm going to go either clockwise or counterclockwise. So let's say I'm going to start with L. I'll do L, M, N, P. That would be how I'd name it. Okay, or I could have gone L, P, N, M, or I could start at any other point and just go clockwise or counterclockwise. Okay, so clockwise or counterclockwise. The no-no would be something like parallelogram. Sorry, there we go. All right, parallelogram L, M, P, N. That would be a no-no. I can't go across like that. All right, it's going around clockwise or counterclockwise. So I just talked about a parallelogram, but the definition of a parallelogram is that the opposite sides are parallel. All right, so we've got ourselves a parallelogram, and remember the way we notate parallel lines is with a couple arrows. These would also be, boom, we've got ourselves a parallelogram. And the way we're going to write these definitions, and upcoming next would be theorems, or coming up next, there we go, would be if parallelogram, then opposite sides parallel. Okay? Opposite sides parallel. And here's the thing, is this will actually work both ways. We're going to get into proving parallelograms next. So given some information, we prove that it's a parallelogram. Or given some information, we'll prove that it's a rectangle, so on and so forth, as we get into different quadrilaterals. So this will actually work both ways. Okay? If it's a parallelogram, the opposite sides are parallel. If the opposite sides are parallel, then it's a parallelogram. Woo! All right, so we've got four new theorems associated with parallelograms. And really these kind of just go along with our definition of a parallelogram, that we're going to use these in proofs, and they will work either way. Okay? These will work either way. So, if it's a parallelogram, we know we have their opposite sides parallel. Another one would be our opposite sides are congruent. We also have opposite angles congruent. Dang, that's awesome. The next one we have is consecutive angles sup. Meaning like this angle here is sup to this angle right here, okay? So as you work your way around clockwise or counterclockwise, pairs of angles are supplementary to each other. All right? Let's see here. We also have that our diagonals bisect each other. Diags bisect. All right, so really if I tell you something's a parallelogram, it comes with so much other information that you can use. Granted, you have to say it in the proof, but if I tell you it's a parallelogram and you want to say something about the opposite sides being congruent, like that would help you in your proof, all you would do is say if it's a parallelogram, opposite sides are congruent as your reason. All right, and our definition will go along with these. Our definition will go along with these, and we will write them in this fashion, okay? No real shortcut beyond what we see here. Cool? One thing that I do want to add in here that you can write in your notes right now, but we'll officially cover it tomorrow, is a way to prove that it's a parallelogram. If you have one pair of opposite sides congruent and parallel, then it's a parallelogram. One pair of opposite sides both congruent and parallel. Meaning if LM was congruent to NP and LM and NP were parallel to each other, then you'd have a parallelogram. Okay? This isn't really necessarily a property of parallelograms, but it's a way to prove that. We will officially go over this tomorrow, but I think it'd be helpful to write in your notes right now. It seems rather nice for organization. Alrighty? Cool. So this example here says using only the definition, prove that in a parallelogram each pair of opposite sides are congruent. So basically we're proving one of the theorems from the page before. Now I'm not actually going to go through the whole entire proof. I just want to go over the concept of it. So if I have a parallelogram A, B, C, D, I'll throw these diagonals in here. The definition is just that opposite sides are parallel. That's it. So that's really all I've got for my information here. And I'm going to prove that theorem. Now some of you are like, well, if it's parallelogram, then the opposite sides are congruent. I know that. There's a theorem. We are proving that theorem. Okay? So we don't have that information. The only information we have are these opposite sides are parallel. But we can prove it from that. It's actually a very lengthy proof. Or kind of, it's not too bad. But it comes through our congruent triangles. So if I've got parallel lines, I know I've got congruent angles. Okay? So I would know that these two are congruent based off of AC being my transversal, AB and DC being my parallel lines. And the same idea can be used to get a couple other pairs of angles. If I had AD and BC as my parallel lines, AC still is my transversal, I've got alternate interior angles here and here. So let's mark those. So these are both pairs of alternate interior angles. And then looky here, we've got AC congruent to itself. I've got a side angle side situation going on here for these two triangles. And once I've got that from CPCTC, I can get my AD and BC congruent, AB and DC congruent. I've got my opposite sides congruent. And I can do that all day with all four of those theorems. I can prove all four of them. Remember, theorems have to be proven. Okay, proven, proved, something like that. Alrighty, cool. So that's the general idea of it. You can see it keyed online if you'd like, but we're going to move on to some of the problems. Alrighty, we got our next example here. Some of the font was a little messed up, so that's why you see some handwritten stuff there. We were given three angle measures, as algebraic expressions, and we want to solve for the measure of angle K. All right. So, and also I'm given, I forgot to write that in, given parallelogram MOPK. So I'm given that it's a parallelogram. Well, what do I know about parallelograms here, especially when I'm talking about their angles? Well, I know that their opposite angles are congruent from my theorems, one of my four theorems. I also know that consecutive ones are supplementary. So like K and M are supplementary, M and O and P and K. Those are all supplementary angles. So I'm going to use that in some way, shape, or form. So let's see, I've got M is x plus 3y, I got O is x minus 4, and then I've got P is 4y minus 8. Well, none of these have like just one variable where we can match them up and solve other than O. Otherwise, they got x's and y's. So it looks like to me with two variables, system of equations is going to be the way that we have to go with this one. That didn't work. Okay. So let's see here. I know that M and P are congruent, right? So I'd have x plus 3y equals P, which is 4y minus 8. Okay, so that's one thing. Let me set that up as a nice system of equations way. X minus y equals negative 8. I just brought that over. That's going to be one of my equations. I got to set something else up. Well, O and K are congruent, but I don't have anything to match that up with. Looks like I might need to use my supplementary aspect of things. So how about M and O add up to 180, because they're supplementary. So x plus 3y plus x minus 4, so that'll be what? 2x plus 3y minus 4 equals 180. So I'd have 2x plus 3y equals 184. So there's my other equation. I got that by adding M and O together. Alrighty, I've got to solve this system. Let me see if I can get some room over here. So I have x minus y equals negative 8, and then I've got 2x plus 3y equals 184. Okay, Well, nothing can cancel out right now, but if I multiply that top one by either -2 or by +3, I'll be good to go. I'll do -2 and cancel out my x's, okay? So I'll have -2x plus 2y equals 16. So these guys will cancel, and I'll be left with 5y equals 200. Yeah, I think that looks good. I didn't make any mistakes with my negatives, I don't see. That's wonderful, always good. So 5y equals 200, y is going to equal 40. All right, so we've got y equals 40. How do I get my x? How do we plug back in? I'm going to use this top guy right here. X minus y equals -8. If I throw 40 in, I'm going to have x minus, x 40 equals -8. So if I add 40, I'll get x equals 32. So that's my x and my y. Is that what it's asking for? No. It's actually asking for the measure of angle K. I don't know anything about K. Oh, wait. Yes, I do. It is opposite the angle O, which means that it is x minus 4 because they are congruent. So if I find O, which is 32 minus 4, that's 28, I know that the measure of angle K is also 28 degrees. So looking back on this problem, I feel like maybe if I was paying more attention to the final final question there, I would have just solved for x first off because I don't have to worry about y. So maybe I would have, instead of multiplying by -2, it would have been smarter, saving time, to multiply by 3 to cancel out my y's, just solve for x, plug back in here, and I finish my problem. All right, so sometimes you'll notice little things if you look ahead, save a little time. I didn't that time, but maybe you did, and that saves some time. But otherwise, we should get 28 either way. All right, we got ourselves a little parallelogram here. Usually you'll see a B, C, D as a parallelogram, or you might see like this, and then you won't see that, which is nice. So like we just draw a little parallelogram. Either way is fine though. Okay. So if it's a parallelogram, I've got all those theorems. I've got opposite sides congruent, opposite angles congruent. My diagonals bisect each other. The consecutive angles are supplementary, and the opposite sides are also parallel. I don't think I mentioned that one. That's the definition. So I've got all that I can use, but I do need to state it. Okay? So I've also got that AF is congruent to CE. And I want to prove that DF is parallel to EB. So let's think about how the heck do I prove lines parallel? Well, I need congruent angles if I'm going to prove lines, prove lines parallel. Alright, so I need to think about that. I'm thinking maybe some congruent triangles to get me congruent angles by CPCTC, which will allow me to prove my lines parallel. So let's see what information we got. If I've got parallel opposite sides or congruent opposite sides, I've got a whole bunch of things I could do here. How about I've got some numbered angles? Maybe those are important. I could probably prove that these are congruent, right? If I state that these guys are parallel, because opposite sides are parallel, then 1 and 2 are alternate interior angles with AC being my transversal. Okay, so I've got an angle and I've got that side, right? So is there anything else I could do? Ooh. Opposite sides of a parallelogram are also congruent, right? Booyah. Those sides are congruent. Now I've got a side angle side situation happening with those two little triangles. Well, if I've got those two little triangles congruent, I'm pretty sure that these angles are congruent by CPCTC. And if I'm looking at DF and EB to be parallel, what type of angles are those? Well, with AC, those are alternate exterior angles, and boom, I've got parallel lines. I'm already done with this proof. I think we can write this up. I'm going to get rid of a couple things on here so there's a little less to deal with. Okay, let's do it. So I've got my given. Then I've got, let's see here. I wanted to prove that the opposite sides are parallel, so AD is parallel to BC. If it's a parallelogram, then opposite sides parallel. That's technically the definition of parallelogram, but I'd rather you guys write it out because you might accidentally write definition of parallelogram for something that's not the definition. That's no bueno. So since those are parallel, I know that angle 1 is congruent to angle 2. If parallel, then alternate interior angles congruent. Awesome. Let's keep it moving. I also know that AD is congruent to BC. If it's a parallelogram, opposite sides congruent. And now I've got my congruent triangles. So I picked those two triangles. The main idea was, well, I've got this already, congruent, so that's a side of that triangle. I also have those numbers, which they're always going to be there, but that kind of clued me into it. And then I can kind of see those triangles forming already and have those opposite sides, right? But the main thing was what I circled up there, AF congruent to CE. Those two sides made me think, all right, I'm thinking these two triangles. All right, so I've got triangle ADF, we'll go with that one, is congruent to triangle, make sure these line up now, C, because that's associated with the angle 1 and 2. D is going to go with B, and then E will go with F. All right, so I've got my triangles congruent by side, angle, side. I need a little more room. Okay, now that those are congruent, I'm going to label these as, how about 3 and 4 for my two angles. That's a better 3 and a 4. Okay, 3 and 4. So angle 3 is congruent to angle 4, C, P, C, T, C. And then lastly, I've got my prove. So DF is parallel to EB. My reason is, well, if I got exterior angles congruent, alternate exterior angles congruent, then parallel lines. Booyah! Mic drop, as they say on the streets of Huntley. Alrighty, there we go. That was a fun proof. Again, if you're using anything from it being a parallelogram, you need to state it. All right, that's what we did here in steps 4 and also in 2. We had to state what we know about a parallelogram. It's not part of the given. The parallelogram is, but we still need to state what we use. All right, lovely. Homework, dogs. Fun stuff.